Thank you all for coming to another discussion hour. We're excited to welcome Dr. Manuele Faccenda. He's an associate professor at the Geoscience department at the University of Padova. His research addresses multidisciplinary and across-scale topics through combined thermomechanical, petrological, and seismological modeling techniques, including geodynamics, seismology, and geophysics for natural risks and resources. So we're super excited to have Manuele here to give us a talk, and I'll let you go ahead and take it away.
Thanks for a very nice introduction and for having me today here. So basically in the next 45 minutes or so, I would like to show you this approach that we have tried to develop to pursue a lot over the last few years with a bunch of colleagues that you can see here. Some of the names, most of them are not anymore in Padova, okay? But and then some others are from the INGV Institute, which is the National Institute for Volcanology and Geophysics. And so basically with this approach, we have tried to combine geodynamic and seismological modeling to better reconstruct the earth dynamics and structure. And this is because usually, with the seismological methods, we get a view of the present day structure, right, of the earth interior, but very often the interpretation of the anomalies or anisotropic patterns is not unique, right? And so you need maybe to have some geodynamic model to help you constrain these anomalies. On the other hand, geodynamic model allows you to reproduce the dynamics, right, given tectonic settings or even at the global scale. However, also there, the lots of parameters are not well constrained, especially geological parameters, and so you can get lots of different solutions by varying the parameters, and you need to constrain these results, usually with observations, and usually we use seismological observation to constrain these models, right? But these, let's say, two-way communication of these two disciplines has not been developed or used a lot so far. Now, how to combine these two methodologies? So basically, you can do this chiefly by looking at fabrics. Yeah, so fabrics that develop due to deformation. Okay, so and then affect the elastic properties and so the propagation of seismic waves. Okay, so fabrics which can be due to the differential alignment of intrinsically anisotropic crystals, like for example in the mantle olivine, in the upper mantle, right, which is the most abundant phase, and it's quite anisotropic, as you can see here. So basically, if the mantle rocks experience deformation, which is accommodated by creep mechanisms like dislocation creep, basically the rock develops a fabric, so a preferential orientation of these crystals that you can see here, right? And the elastic properties becomes anisotropic, right? With the velocities like Vp, which is varying with the propagation direction. These are equal era projections, also all figures, right? And you have also the phenomenon that I'm sure that you're aware of is shear wave splitting. So basically, a shear wave, when traveled through an anisotropic medium, it will split into components, orthogonally polarized. And so you have the fast component, which arrives earlier, and then the slower component, which arrives afterward. Other mechanisms that can produce this variation of the seismic properties with the propagation direction include the presence of fracture, preferentially aligned fracture within the lithosphere, mostly in the crust, okay? Or, for example, the formation of porosity bands in a partially molten rock. If you deform this rock, basically you can form these porosity bands, right? Or the presence of compositional heterogeneities at the rock scale, like this is an ophiolite exhumed in Oman. You can see this layering of dunitic and aspergitic, so more fertile layers, or at the grain scale. This is nice. You can see nice foliation and lineation due to the deformation of, so defoliation is given by weak mica and quartz crystal, which absorb most of the deformations, while the strong plagioclase and feldspar, they form these elongated cigars. So this mechanism which are due to the shape preferentiation of structures with contrasting isotropic elastic properties, are referred to extrinsic or apparent anisotropy, because you can form anisotropy even if the material is isotropic. And so this is due to the contrast in isotropic elastic properties. That's why you get this anisotropy. But we have shown that, for example, these two mechanisms, they cannot produce a considerable seismic anisotropy in this paper here. Why? Because the contrast in isotropic elastic moduli is not that high, right, in minerals or different rocks. And so the anisotropy is really negligible. While toward the end of the talk, I will show you an example where cracking and fracturing in the lithosphere can really produce very high seismic anisotropy. Anyway, so how can we determine the dynamics of a given system from seismic anisotropy? Well, we know that when the mantle deforms, like for example, here we are in an intraplate setting, there is a acidic lithosphere which is sliding and is imposing a simple shear deformation within the underlying asthenosphere. So the fabrics can form, right? And you can get shear wave splitting. So if you have a teleseismic S wave that sample these asthenospheric mantle vertically, usually you get the fast component which is polarized parallel to the plate motion, right? So if we manage to measure the seismic anisotropy, and we know the relation between the seismic anisotropy patterns and the fabrics that develop in the mantle, so basically we can reconstruct the dynamics. However, even in this very simple case where the deformation, where the velocity varies only one direction along the vertical, right? So this is the simplest. This is just simple shear deformation, right? The simplest case. Let's say there can be three different olivine fabrics that can explain the same observation, right? These fast Hudson parallel to plate motion. So which means that the interpretation, even in this very simple case, is not unique. And then when you got convergent margins, the situation is even more complex because the flow is strongly three-dimensional. You can have slab windows, stairs, and so on. This is the Mediterranean, which is one of the most complex, probably convergent margin on Earth, right? And so here is where geodynamic modeling comes into playing a big role, because we can try to model the fabrics that develop during this deformational phase, right? And basically test hypotheses and see if a given dynamic evolution of the tectonic setting can reproduce the observations. Okay, so what we need now, this is the workflow. We need a geodynamic model. This is a general model of subduction in 3 dimensions. There is a slab that subduct by its own negative buoyancy here, right? So the white surfaces envelop material with high viscosity, so the slab and the lower mantle, right? This is a symmetry plane. So, run the model, you get this subduction model with the plate, in this case, stagnating in the transition zone. And so here what you need the velocity field, right? The evolution of the velocity field, because deformation depends on the velocity gradient, so the spatial variation of the velocity field. And so you can compute deformation and rotation for this velocity field. And then you need the pressure and temperature fields, by which you can scale the elastic properties as a function of pressure and temperature. Okay, then what you can do here, in this case as a post-processing routine, you can fill up your domain with lots of particles. Each particle is like a polycrystal aggregate with different composition and mineral distribution. So basically, you see here upper mantle is a 70% olivine, 30% orthopyroxene, and then the transition zone with the olivine high pressure polymorph and garnet, and then the lower mantle with the bridgemanite and ferropericlase. Okay, and then what you need another software which models the evolution of the fabrics as a function. Oops, sorry. Go back as a function of deformation, right? You can see here how the the CPO evolves with this is a simple experiment, simple shear deformation, and then you measure the strength of these fabrics, so the strength of these CPO of these peaks, and compare with the experiments, right? You can see that if you tune a little bit the parameters, you are able to reproduce to some degree the experiments. And this is, very large strain, 25 shear strain, which has been reproduced by this the author, Japanese lady. Anyway, so for this exercise, for this modeling, we use the modified version of the DREX software, which basically, so if you download DREX, can only model in 2D with a 2D flow upper mantle. So the evolution of the FPO in upper mantle aggregate. So basically we have extended it to the evolution of the fabric of other anisotropic phases like laterite, Bridgmanite, and recently postperovskite, and so on. Right. So here you have the fabrics, and then as a function of the crystal orientation, volume fraction, and single crystal elastic properties, you can compute the full elastic tensor of the aggregate, and basically you can plot the elastic properties like VP, which is faster, blue here and slower here, DVS, so the amount of splitting that you will get as a function of the propagation direction, the polarization of the fast wave, and so on. Last thing, you need a database that scales the elastic properties as a function of pressure and temperature, right? Because if you do this, then you see you can reproduce RAM, right? If you have a this, let's say, decently good data set of these pressure and temperature derivatives of the elastic moduli, right? And that's the result. So for the model we saw before, we get the full elastic tensor density, and then we can plot different properties of the elastic tensor, like this is the isotropic DVP. You see that here the anomaly are associated with the colder slab, and then here there is some topography of the 410 and 660. You can plot the maximum, the highest, the direction of the fastest P wave, right? So these bars indicate the maximum VP, and the length and color is proportional to the VP anisotropy. Okay, you can plot, calculate and plot radial anisotropy, red positive, blue negative, and you can do also some seismological synthetics. Like in this case, you can compute SKS splitting, right? So you basically need to define a grid of virtual stations, right? And for each stations, you stack the elastic tensor below, and then there is a software which is included in the FS track, which is a software by Thorsten Becker. Right? He led this kind of strategy before than me, and also he helped me a lot at the beginning when I started doing this. And so basically you can do seismological synthetics, right? Now all these softwares that allows you to model the fabrics, plot the elastic properties, and then do seismological synthetics are now included in this software, ECOMAN, which is not a superhero, but it's the acronym for exploring the consequences of mechanical anisotropy in the mantle. And I will show you in a few slides why there are some consequences of the presence of mechanical anisotropy. So basically, once you have the output of your geodynamic model, you can use these softwares here to compute the fabrics due to CPO or SPO, okay, intrinsic or extrinsic anisotropy. Then you get as an output the deformation tensor and gradient tensor and the elastic tensor. If you want also the viscous tensor, but this is another story. You can plot them as I showed you before, and then you can perform synthetics like computing SKA splitting or performing seismic tomographies, isotropic, anisotropic, P wave, S wave, as you want. And you can also use real seismic dataset to perform these tomographic inversions accounting for seismic anisotropy. Yeah, this is first step, plotting, and this is the synthetics. There is also a software for people for those that are unfamiliar with this sort of fabric evolution modeling. So DRX-S is for single crystal aggregate. So you can define the composition, the velocity gradient, the amount of strain, and other parameters which affect the fabric evolution, and model the fabric evolution, only for olivine or just orthopyroxene or combination of the two. You can add SPO, so like melt filter cracks with some orientation and so on. And then here there are some plots of the evolution of the anisotropic properties with deformation. You can do this for any anisotropic mantle minerals. And then there is the DRX-M, which is the multiple crystal aggregates. And so this is the one that computes the fabrics for hundreds of thousands of millions of aggregates, depending on your computational resources, right? And you can do this for any regional, local, regional, global models, 2D, 3D, Cartesian or polar spherical coordinates. Sorry. So here I just show you 3 examples. This is like a 3D plume. This is a toy model, so the plume is really large and so on. But you can see that after you compute the elastic properties, accounting for the formation of fabrics, you can plot. This is isotropic Vs. This is the shear wave splitting. This is radial anisotropy, and this is azimuthal anisotropy. This is isotropic DVS, and then you can plot the amount of energy which is reflected or transmitted during PP or PS. You can use this as a reference, for example, if you're doing receiver functions, right, where you have all these conversions at these discontinuities. So in this case, the resolution here is not that great. So you see that the 660 is imaged with this thick layer, okay, and this is the 410, which of course gets depressed because there's the plume that is hot. Okay, this is a subduction model done a little bit better than the previous one I showed you before. Here you can see, so the green volume encloses material which is faster than 2% for P wave, right? That's the slab at depth, and the radial anisotropy, and on top the computed SKS splitting, right? And then later we have applied this also to global models. So this is a model run by Pulami Roy. We just graduated in the DFZ in Potsdam, and yeah, she has computed the fabrics for the whole mantle for 250 million years time evolution. Basically, the models were run with data simulation technique, where basically you input the plate motions from paleographic reconstructions and so on, like G plates, right? And you can you get the elastic tensor, and again you can plot radial anisotropy here on the left, and this is isotropic DDS, and yes, many other things. Good. After this, if you want to do the synthetics, SK splitting, or you can do the seismic tomographies, right? Using this PSI, which is a platform for seismic imaging. There are 2 softwares here. One is for the classic deterministic inversion, right, where you have the regularization, smoothing, damping, and so on. You need to impose a grid and so on. This was developed by Brandon van der Beek, which was in Padova. We were working together for 6 years. Now moved to Leeds. He graduated in Eugene, Oregon. He got his PhD actually there. And you see, so basically, if this is your target, so these in color here, you get the isotropic anomalies, and the bars indicate the fast P wave direction. This is what you would recover when you do the seismic tomographies. Of course, here we think in this case we put a grid, homogeneous grid of stations. The spacing is 75 kilometers, which is comparable to the US array, right? So conditions which is not natural, but they have, to a first order, even the models, they have a degree of complexity which is comparable in a way to nature, right? Because you have strongly 3-dimensional flow, you account for phase transitions, and so on. So you see that, and this is what you should compare. That's the picture of your geodynamic model that you should compare with observations. Okay, so this is an anisotropic P wave tomography. But of course, you can do also isotropic P wave tomography. if you need, or S-wave tomography and so on. And as I said before, you can also use real seismic data sets. So now recently Brendan has applied this technique to Cascadia, right? So this is the Juan de Fuga slab, I think below 100 kilometers or so, and that's the anisotropic pattern. I think at 200 kilometer depth, and then there are these low velocity anomaly close to the ridge. Okay. Good. So why is this methodology useful? For three main reasons, I think. So the first is, and we just saw an example, is that because you can validate geodynamic models, yielding a physically based interpretation of the seismological observations. So basically, so in Cascadia, so this is the Juan de Fuga plate, which is subducting under the Cascadia trench. This is the Mendocino fault, right? This is the San Andreas fault. And the blue line here is the surface projection of the southern edge of the Juan de Fuga slab. Okay, so the slab is arriving this south, right? And then the red bars are what? Are the fast azimuth of the SKS waves recorded in the area. And you see that they basically follow this circular pattern, right? And the interpretation here from Zant and Jean Humphreys is that this is due to the fact that the Juan de Fuga slab is subducting and retreating in using this toroidal flow cell, right? And basically you get the olivine fast axis that align parallel to this toroidal flow pattern, and basically that's what you're gonna see if you're gonna sample this toroidal cell with the SKS waves, because they see the fast olivine direction, and so the fast component of the after splitting the fast component will be polarized parallel to the olivine fast axis, and so parallel to the flow direction. So with our simple 3D subduction model, you see that we get exactly the same here on the side. Okay, this of course is mirrored relative to Cascadian, because here is on the south, here is on the north of this model, right? Yeah, and here we prove that indeed this circular pattern is due to the toroidal flow, right? That aligns the olivine fast axis parallel to the flow field. You see these are the P wave fast directions, which are parallel to the olivine fast axis. And you see that maybe you see this circular pattern, and then becomes trench perpendicular at the mantle wedge, like, and then you have trench perpendicular polarization of the fast azimuth, which is what you observe also in Cascadia. And so in this way you say, okay, this model is not, maybe it has an evolution which is not that far from the recent evolution experienced by this subduction margin. We have applied the same technique to the Mediterranean. On Thursday, is the fourth lecture, we'll talk about the application, especially the Mediterranean. So here, just give me, let me give you context. So basically 30 million years ago, this is Africa, this is Europe, Adria plate, and this is the Ionian Ocean in between. Basically, the Ionian plate started to subduct beneath Spain, France, so Sardinia and Corsica were also here. And then basically, so this model tried to reproduce what happened afterward. So we put just some initial negative anomaly attached to this oceanic plate, and then subduction evolves self-consistently. So of course the plate subducts, retreats, right? And then something happens when the passive margin interacts with the trenches, and then this segment of the plate continues to subduct, because here there is oceanic lithosphere, right, which can subduct. And so basically here what we can do as a post-processing routine, we can compute the fabrics and then compute the seismological synthetics, FK splitting once again in this case, right? And for this case, this model, I have also we have done a better version of this model because, you know, the model here is closed, has closed boundaries. So basically the fit is kind of good in some regions and also good in other regions. Anyway, we get a misfit of about 26 degrees, which is anyway improvement of what is of basically other models which do not account for the evolution of the deformational history, basically. And yeah, so this is of course an ongoing work. But you see, so basically in this case, you can say, okay, the model is valid up to a certain degree because it can reproduce the observations up to a certain degree. And then we did the same also for the South Central America and the Caribbean subduction system, this time in spherical coordinates. So in this case, once again, we get an average misfit of about 20 degrees, right, which is an improvement to what has been done, you know, using other approaches, you know, before the misfit was much larger. Okay, and the difference is that here we are taking into account for the deformational history, right, and the evolution of the system, dynamic evolution of the system. Okay, the second point for why this methodology can be useful is that we can test advantages and pitfalls of existing seismological inverse methods. So again, we take this subduction model, and basically we perform seismic tomography in this box, where once again we have the elastic tensor, we can do whatever we want, right? Once you produce the P-wave arrival time with some forward modeling. So once again, the isotropic anomalies are characterized mainly by this fast anomaly connected to the slab, some topography of the 410-660, and then this is the P-wave anisotropic field, again characterized by these fast directions which have this circular pattern around the slab edge, and then are below the slab are trench perpendicular. They are, because they are sheared by the subducting plate, and also in the mantle wedge they are trench perpendicular because here there is trench parallel extension. So basically, we have used a real teleseismic event distribution from an experiment in the Caribbean, right? So if this is the target area, we have teleseismic event distributed from 30 to 180 degrees angular distance, right? And here in this pole projection, you can see how so these are all teleseismic events, which will sample our domain that we want to illuminate subvertically, basically. Okay, because you know, the teleseismic phases travel like this, and then when they arrive to the target area, they mostly travel subvertically. And so this means that we are sampling the medium preferentially in one direction, which is close to the vertical. Okay. Now see what happened. Okay, this is when we have performed the forward modeling. So we have computed the travel times and also the inverse modeling, assuming that so excluding the anisotropic component of the elastic tensor, right? So in this case, if there was no anisotropy, basically you see that you can reconstruct the shape of the slab. These are two vertical cross sections, okay? And also these are four horizontal cross sections. So you do manage to reproduce to a certain degree the shape of the slab, right? These are two blocks. This is oceanic crust and just been dragged down. Now, this is what happened when we compute the travel times with the full elastic tensor that has anisotropy on it, but we assume the medium is isotropic. So we do not invert for seismic anisotropy. So what happens is that when you use only teleseismic events, so you see that you do still manage to retrieve the shape of the slab, more or less, okay? Why? Because the temperature difference between the slab interior and the surrounding mantle is so high that you develop a true strong isotropic velocity anomaly, okay? That's there. But all around the slab, you see that there are all these low velocity anomalies. These are artifacts, and these are due to the fact that we are ignoring for seismic anisotropy. Okay. Why it's like this? Because if you have a fast axis, which is subhorizontal, you are sampling it with the teleseismic phases, so vertically. Basically, what you're gonna do, you're gonna sample the slow axis, right? You don't see the fast axis. You only sample the slow axis, and that's why you get this low velocity apparent anomalies, which of course will bias our understanding of the Earth interior. This is when we have used only local earthquakes. So basically, this is a work led by Max Besada. And basically, he has put some random seismicity within the upper 300 kilometer of the slab. And you can see that in this case, you can still see the upper portion of the slab, right? But above the slab, you see that there is this a strong low velocity anomaly here. There is some high velocity anomaly. Okay, these are all apparent anomalies. Okay, because the only true anomalies is the one related to the slab. Why it's like this? Because when you have subduction, right? Subduction uses poloidostrope, right? So it shears the mantle, right? So it drags the mantle down, and other mantle is pulled over, sucked into the mantle wedge. Right? And so you have to imagine that the fast axis of olivine orients parallel to these streamlines. Okay. And so here, imagine you have events here which travel like this. So here you will send the fast axis is parallel to slab dip. So here once again you're sampling the slow direction. Right? You get the apparent slow velocity anomaly, which unfortunately sits right above the slab where we would expect some melt or fluids to be there, right? And then when you start to go here, you start to see that the waves start to see the fast axis, and then you get this apparent fast anomaly. What is it? Is it a lithosphere dripping, right? No, actually, this is again an apparent anomaly due to the fact that we are not accounting for seismic anisotropy. This is when we have done the inversion with the joint datasets of teleseismic and local seismicity. And again, you do see the high velocity anomaly related to the slab, but still you see lots of low velocity anomaly above and below the slab and all around. And so the provocative question here is, are all seismic anomalies real that we do see in the tomographic model? Because you see that so the slabs are here, and they are constrained by the Binov, but are the Binov planes, and I have no problem with them. But all around the slabs, you have all these low velocity anomalies. They might be real, or in some cases they might be artifacts, right? Just want to show you an example. So this is a quite famous, popular P-wave velocity model from Cascadia. And this model was generated with teleseismic phases, right, P-waves. And so here you see that you get, in this section, you can see very well the Juan de Fuca slab, and then these are two vertical cross section. You see the Juan de Fuca slab, but around the Juan de Fuca slab, there is this low velocity anomaly, right? How would anyone interpret this low velocity anomaly? With something hot or partially molten, which is buoyant and which is sitting below the trench, basically the bending, the other rise bending area, right? I would have done the same, right? But here in Cascadia, if you remember, there is a lot of anisotropy. So the SK splitting goes up to 2 seconds, right? Which means that there is seismic anisotropy in the mantle, and if you do not account it for, you may get these low velocity artifacts, which they look not so different from these. I mean, these anomalies, they might be real, okay, but probably we should try to test their presence to validate them with maybe using the surface waves, which sample the medium in a different direction. Yeah, and with other informations and so on. Okay. Yeah, you see that the similar situation occurs here in the Western Alps, This is the European lithosphere, which is subducting toward the southeast, and below there is this very strong low velocity anomaly, which is this one, right? In this case, this low velocity anomaly was explained with magma or hot mantle coming from the Massif Central and being somewhere flowing in this direction. You know, this is a region with very strong anisotropy as well, which has not been included in this study. And so, yeah, you know, we need to better validate if these anomalies are real or not. I think that's the message. And the same thing in other subduction zones. Okay. Yes, okay. And then we can also test new inversion methodologies that try to account for seismic anisotropy, right? Because at this point, we know that if you do not account for seismic anisotropy, and we know that seismic anisotropy is widespread, right? At least in the upper mantle, then we gonna incur in potential problems with all these artifacts. And so the problem is that so far, seismic anisotropy has been accounted for with, for example, with SKS splitting or PN anisotropy. So PN are these phases that just are refracted at the mole and sample the upper portions of the lithospheric mantle, right? Or surface waves and so on. Now, all these, I would say, all these observations that either gives us a projection of the anisotropic field on the vertical or horizontal plane, and this is especially true for surface waves because usually they produce these tomographic models where they invert for radial anisotropy or azimuthal anisotropy, which assume transversal isotropic medium with a vertical or horizontal symmetry axis, right, and no more than that. SKS observations are path integrated, so you don't know where the anisotropy exactly is, right? And so basically, what we are trying to do is to develop a method which basically is capable of inverting for a tilted transversely isotropic medium. Okay, so transversely isotropic medium is this medium where basically you have the velocity which are the same on a given plane, which can be fast or slow plane, and normal to it there is a symmetry axis, right, which can be fast, right, if the plane is a plane of slow velocity, or slow if the plane is of fast velocities. This is the simplest anisotropic medium that you can think of. It's like when you have a layered medium, right? And so the symmetry axis will be perpendicular to the layering, right? And the problem is that so far, I think only another group was able to do this inversion, assuming that the symmetry axis, so this transversal isotropic medium, can assume an arbitrary orientation in the 3D space rather than just vertical or horizontal, right? And so basically, if this is our target, once again, subduction model, isotropic anomalies, this is the P wave anisotropic field. Okay, this is two different horizontal cross sections. These are two different vertical cross sections. So here the dataset, synthetic dataset, is being computed with the spec fem and axis m. It's a station distribution and so on. Okay. Okay, that's basically what you get. These are these first inversion with it. This is when you ignore for seismic anisotropy, and you get these strong artifacts around the slab. This is when you do account for a seismic P wave anisotropy, and so these artifacts are attenuated, right? And plus, you are able to reconstruct at least part of the P wave anisotropic field. Okay, especially these circular pattern here, and also the dipping portion of the fabric. So basically, if this is the target, this is what you manage to recover. You do not manage to recover the horizontal portions of the lithosphere, because here we are only using teleseismic phases. And so if you have a horizontal anomaly, it's difficult for the vertically traveling teleseismic phase to locate this vertical anomaly. But if it's dipping, and then we manage to recover it. Oops. yeah, we have done the same also including S-wave, right? And basically you see, this is when you ignore for seismic anisotropy. This is when you assume that the symmetry axis is horizontal, so it's just azimuthal anisotropy. And then this is when you allow the transverse isotropic medium to be oriented in any direction, right?
Manuele, may I ask a question about that?
Yeah.
Because you mentioned earlier that you had an hexagonal elastic tensor, right, elastic medium,
Yes.
when you talked about the P arrivals. So there is not just P or S anomaly, there's only elastic anisotropy. Is it not the same elastic model that you use both for P and S arrivals?
Yes. Yes,
Okay.
we do. Yes.
Okay.
So basically, the elastic properties come from the
From the geodynamics, for example.
geodynamic
Yeah.
modeling,
And
right?
you test them both against P and S arrivals.
Yeah. Then we start with P wave, and then we also included S wave. But this is mostly the work by Brandon van der Beek,
Yeah, but
right?
so it's the same elastic model.
Yes.
Okay.
This is the same elastic model.
Yeah.
Here you see same inversion only using P waves.
Yeah.
This is only using S wave. This is the joint
Yeah.
inversion. Okay. And with S wave, basically, they are more sensitive to the shallowest layers, and so you get a better resolution at shallower depths relative to the V wave. While the V wave are more sensitive deeper down. Okay, so when you invert for both, you get something like the better representation of the anisotropic field and of the isotropic anomalies. Okay, this is just to say that we have applied the P wave isotropic tomography to the Mediterranean, and I will talk more about this on Thursday. This is for example, you see here, this is the Aegean slab. So these are this volume encloses material which is faster than the threshold, and we interpret that as the subductive lithosphere. And then here you see this is the P wave anisotropy at 200 kilometer depth. You see here the parallel to the tip of the Aegean slab, there is the P wave fast axis, which is parallel, and this probably due to the fact that the slab is going down, is shearing the mantle and aligning the fast axis of volume in this direction. This is, you see there are tears. This is the slab subducting below the Balkans. This is the Alpine slab, Alboran, and here you can see the Ionian plate, which is subducting under the Northern Apennines and under Calabria. With this slab window, this is imaged by many other tomographies, and basically in this part of Italy was interested over the last million years by lots of magmatism, which is consistent with this window, right? And the fabric here, you can see that below the slab, the fabric is trench parallel and is flowing from here toward the trench, the mantle wedge, sorry, where it turns into trench perpendicular. This is for Calabria, you see, trench perpendicular mantle wedge, trench parallel below. So there is some consistency with the models. Okay. All right. So, and then I would like to spend the last 5 minutes. I'm already at 45. Sorry. This is a recent work that we have been working on over the last 1.5 years. This is a project by PhD candidate Gianmarco De Piccolo, who has developed the stochastic version of the platform for seismic imaging. Now, before there was the deterministic code, right? And this is the stochastic version where basically we perform transdimensional Monte Carlo events, and we apply to the imaging of the Etna volcanic field. These are the stations monitored by the INGB Catania, so the Etna Observatory, and this is the seismicity, which is deeper a little bit this side. So this is a very good margin, right? This volcano sits on top of a continental collision, right? Then next to it, there is the Calabrian slab, which is retreating. And so here there is an active convergence, right? So there are thrusts and so on. And still there is this volcano, which has formed over the last 500,000 years. And the eruptions are quite frequent. It's quite active volcano. So here in this case, we have discretized the model space with Voronoi diagrams, right? And each diagram has a constant, in this case, velocity, velocity anomaly. And then there is another Voronoi diagram tessellation for the anisotropic field, right? So each parameter that you are inverting for, isotropic velocities, anisotropic patterns, they have a distinct Voronoi tessellation. So basically here the parameter space is investigated in a probabilistic way. So we test millions of models for each of the 112 independent Markov chains. Okay. And basically the advantage to the classic deterministic method is that here in this case, even the grid is an unknown, right? So basically at each iteration, you have different choices. You can move the nuclei of one Voronoi cell. You can delete one Voronoi cell, or you can add a Voronoi cell with a different elastic properties. The only thing you need to do is to define the priors, so the range of likely values that parameters can have. Like for example, for the seismic velocities, in this context, you would say, okay, seismic velocities. Velocity, actually in this case, we start from 1D model, and then we say, okay, the velocity can vary by plus minus 15 or 20%. I remember here the range of this prior. Same for seismic anisotropy. So the medium can be anisotropic, can be 0 isotropic, or up to 20-30%. Okay, and then what the model does through the iterations, basically you test different values of the P-wave anomaly or of the anisotropy, right? And try to decrease the misfit between the observations and what you are modeling here, right?
So this doesn't do the tilted transverse isotropic?
Yes, it does.
It does?
It does. This is just a projection on this cross section at 1 kilometer depth. Okay. So once again, you see that all the different chains have a different model, right? And in the end, what you can do, you can calculate the statistical moments like the average and standard deviation, right? And so if you have, the standard deviation, you can infer areas with a small standard deviation. So where basically lots of models require that value of anisotropy or of isotropic anomaly, right? And so you say the uncertainty is small here, and I trust this region of the model. And you can discard regions where the spread, right, of the value of a given value is very large. So the standard deviation is very large. Okay, this means that you have an estimate of the uncertainty at each point of your model, right? So here, what you see, these are low uncertainty VP anomalies. Okay, so in blue, these are fast VP anomalies. Where low uncertainty here, we assume that low uncertainty is with less than 60% relative standard deviation. The high velocity body, so here there is this high velocity body that goes down to 6 kilometers, and this is seen in many other tomographic models, and is interpreted as the old part of the volcano, which has crystallized and solidified. So these are basalts which sit next to sediments. So there's a contrast, high contrast in velocities. That's why you see this high velocity body. And below it, between 6 and 16 kilometers, there is this elongated low velocity body with some branches, right? But this is the biggest low velocity feature we see in this model. Now, if you look at the anisotropic field, this is more interesting, because below the high velocity body and down to 16-20 kilometers, we see a cylindrical pattern of the P-wave slow axis. So in this case, we assume that the symmetry axis of the TTI medium is the slow direction. And we have arguments for this, right? So you see that there is this cylindrical pattern, which is not centered relative to the demographic peak, but it's more. It is centered more toward the southeast quadrant. Okay, basically around, you'll see around this low velocity body. you can see these two cross sections. You see this circular pattern. So we can compare these P waves or directions with the t-axis of local earthquakes. Usually t-axis can be interpreted as direction of minimum stress, right? You can see that also this t-axis, they have this circular pattern, which is not really centered with respect to the topographic peak, but it's displaced a little bit this direction as our cylindrical pattern of the P waves axis. So now how to interpret these observations? So we have a P waves directions with this cylindrical pattern, which is similar to the orientation of the t-axis of the minimum stress, and then sort of is very high, 10-20%. And so we think that this pattern is due to the preferential orientation of magma-filled fractures, cracks. Okay, why? Because if you have this arrangement of cracks, the P wave slow direction would be normal to the cracks, right? And you know the cracks open, right? Will open in this direction. So basically, the t-axis, the tensile axis of the stress field, will be also parallel to the P wave slow axis. And so now, if we plot the planes normal to these slow directions, we should get the orientation of the cracks, right? And that's what we have done here. So these are the P wave slow directions, and these are the fast planes normal to the slow direction. And you see that if you have a cylindrical pattern, like tangential pattern of the slow axis, you get a radial pattern of the fast planes, which are more, you know, the color and the size of these planes is proportional to the amount of anisotropy. So it looks like it's higher here where there is the high low velocity body, and then they depart from here. Yeah, this is just to show you an animation. These are the fast planes. These are the isotropic P wave anomalies. Yeah. So below this high velocity body, there should be this low velocity body from which all these cracks should like they are departing from. And yeah, so here that we can use geodynamic modeling to explain why it's like this. You can take into account the effect of topography, tectonic stress, or the presence of magma storage, in which you can inject magma from below. And basically, you can see that if the magma storage has this prolate shape, you get the cylindrical pattern, right? This is the minimum stress of the t-axis that you develop here, right? And if you want to get magma storage, which is more similar to the low velocity body here, so then you need to have this oblate shape of the magma storage. And again, if you pressurize it, injecting magma in it, so basically you can have this circular pattern. Here there is also the contribution of tectonic stress, topography, and everything, so you can account for all these different stress sources. Right, so we do think that this cylindrical pattern is due, reflects the presence of a pressurized magma chamber from which all these radial dikes, radially distributed dikes are departing from. Yeah. Last slide. Okay, so in the end, okay, during this seminar, I hope I've convinced you that coupling geodynamic and seismological modeling is a good strategy for better understanding the earth dynamics and present day structure. And this is a methodology which can be useful to validate geodynamic models, yielding a physically based interpretation of seismological observations, the interpretation of which is not unique, as you know. Test advantages and pitfalls of existing seismological inverse methods, and test new inverse methodologies which are capable of accounting for seismic anisotropy. Thank you, and sorry for being a little bit late.
Questions? I know we've got a handful of people on Zoom, so if anyone on Zoom wants to just unmute and go for it, go ahead.
Just have a quick question. So this is more of a curiosity thing. So how does mapping Etna, I guess, I've seen several papers where it's like, oh, this is an inner plate volcano, or, oh, this is like a, you know, subduction related volcano. How do you think this work will help, I guess, answer some of those questions, like maybe it's, the way it's plumbing is tied to the rest of the volcanic system in the area?
Well, what these studies, I think, tell us is that so Etna is a very active volcano. You have lots of lateral volcanic vents, right? So most of the eruptions are toward the peak, but there are many other which are occur on these lateral vents, right? So I think you know the common view of the volcanic plumbing system is that you have these magma storages, more than one, and then you have these conduits which connect them and eventually arrive at the surface, right? Okay. But what this model is telling us that actually the magma is distributed over much wider area, actually over almost the entire volcano, and which could explain, for example, the occurrence of these lateral vents. And plus, once again, how can you produce these dikes so far from the magma storage? I mean, this tells us that the stress state of the volcano is characterized by this pressurized magma chamber, right? Which explains also why you have these very frequent eruptions. Right? So you have this pressurized magma storage that continuously expels magmas and so on. Then there is a major unsolved question here where this magma is sourcing from, is produced. We don't have the data here because we are only using level seismicity, which can be deep as 30 kilometers, but only on the northwestern quadrant. We cannot go deeper than that. Then you need to use maybe seismic phases and other things, but of course then the resolution decreases. So we cannot answer everything. But what the picture here, what looks like is that the crust here is really heavily fractured, and the fluids are distributed a bit everywhere over the system. Yeah, let me if I actually answer your question. Yeah, sorry. Yeah.
I was wondering, for example, I have two questions. And first is for in subduction region, and you mentioned that is the result of the low velocity anomaly and the slab could be caused by the seismic anisotropy phases. I was wondering, do you think how large is the seismic anisotropy can cause such kind of slow velocity anomaly? And based on the,
On the observations.
Yeah.
Yeah, this is a question I get quite frequently because people think that the anisotropy that we model is a bit too high. Okay, but actually we have so now that we are inverting for seismic anisotropy here. We get anisotropy which can be a few percent, up to 4, 5, percent in some areas, but here we are applying smoothing and damping, right? Which means that the true anisotropy is even higher than what we have resolved in this model, for example. Okay, because this is an inversion done with the classic deterministic approach where you need to apply regularization. And so you apply damping, which means that you are trying to stick to the initial 1D model, which is often isotropic, and then you apply smoothing, which means that you are spreading your local anomaly laterally. Okay, so I think that in reality, the amount of anisotropy, it's even for P-wave anisotropy can be 5-6% in the mantle. Okay, and this is enough to cause these low velocity anomalies, because low velocity anomalies, if you look at the tomographies, usually are a few percent, 1-2%.
You mean for the Cascadia one?
Yeah, here it's more, okay, plus minus 3%. Okay, and here is plus minus 2, plus minus 0.8. Okay, and you can produce these anomalies with a few percent of P wave anisotropy.
Okay, so for your setting, I mean, for such kind of the mental convection things, you must have said that as seismic anisotropy originally come from the Olivan anisotropy, and typically for the, yeah, mostly for the Olivan mineral anisotropy, it could be very high, and since, I mean, it's 20%, more than 10%. And for your outcome of your program, and typically it will just generate the observable of just 5% of P wave anisotropy. So does that mean, so you mean probably you apply the smoothing and damping and based on the wavelengths? I mean, it's based on the data set you want to fit, or
I'm not sure. So the question. So what I was trying to say is that.
So I just, for example, for your model, for your setting, I mean, do you set how large Olivan seismic anisotropy do you set?
In the geodynamic models?
Yeah, yeah.
There you can go up to, let me see, the 6%.
6%?
Yeah.
For you mean, how large is element? Is that for a single Olivan or is
you can
it
see
for?
here, look, the bars are, the color and length is scaled according to the amount of P wave anisotropy. So red means 6%.
Okay.
And that's what you get. But it's true that these micromechanical models that are used to simulate the fabrics, they tend to overestimate a little bit, right? And this is why we have spent time on calibrating the tune the parameters to trying to reproduce the fabrics, the strength of the fabrics at very large strain. This is 25 strain. Okay, so you see. This is what they measure. What we reproduce is a little bit higher, but still you see that this is when you use the classic direct parameter, you get anisotropy which is super strong. But then if you start to tune the parameter, you can predict much less.
Yeah. And another question is, so in your setting, I'm curious about the viscosity things and
Viscosity.
Yeah.
Viscous anisotropy. No, what?
I mean, yeah, for example, I mean, say if I have a faster axis, which is along the east-west, and do you think how many years can I, if I just want, based on your viscosity setting, can I take 90 degree?
Okay. So usually, there is Agnes Kirali that has worked a lot on this. There's a geodynamicist colleague from the University of Oslo. So usually it has been shown experimentally by this American mineral physicist, tell you in a second, but anyway, that you need strain up to 5, okay, to erase the previous fabric and form a new one. Okay, so, but I can show you a paper by this colleague, Agnes Kirali, they exactly did this. So they had some pre-existing fabric, and then with some simple plate motion, they try to see how long it takes to reorient, right? Yeah, if you're interested.
Thank you.
Yeah. This is the mineral physicist from St. Louis University, Washington.
How is it, St. Louis?
Yeah.
Philip Schimmer. I thought you were talking about last six with him, if you're not.
No, Philip Schimmer.
Phil Schimmer, yeah.
He has a few papers on this. Pretty cool.
It's Washington University, St. Louis, yeah.
Washington University, St. Louis, yeah, sorry.
I have a couple of questions too. So the one is you talked a lot now, of course, you talk about calibration. Of course, you have laboratory data that can go into that, of course, geodynamics, seismology. So you have very complicated subduction models, and the amount of anisotropy that you're showing, they actually are quite similar to the anisotropy that we see in mid-ocean ridge systems as well. Because you could have in the Pacific fast spreading range, you could maybe get up to 5% as well. So I was wondering if that is an important calibration kind of geodynamic setting for you, if you're trying to understand like how anisotropy is produced by strain history, maybe some stress state, is the much simpler setting of a subduction, of a
Yeah.
corner flow in the mid-ocean ridge system. Is that an important calibration system for you?
Of course it is.
Yeah.
And, yeah, you know, people know me mostly because I work a lot on subduction,
Yeah, I
but
know
more
that,
recently
yeah.
we are also trying to reproduce, you know, I have reproduced this, divergent margin and then a
Yeah.
plume setting. And so
Yeah.
here, you know, the subduction zone.
Yeah.
And, we have applied this, P wave and S wave, anisotropic tomography to these three different settings.
Yeah.
You know, ignoring for anisotropy or just assuming, you know, azimudal anisotropy or TTI medium with the separate P and S inversion or joint. So, yeah. And the problem, so you mentioned the ridge, right? Look what happens.
Sure.
So here, the only true seismic anomaly is due to the fact that you have lithosphere here, which is
Right,
cold.
yeah, that's right, yeah.
And then here it's a lower velocity, right? The hot mantle. Now the anisotropy, so the ellipses are proportional to the amount of anisotropy. So the maximum axis of the ellipses is proportional to the amount of anisotropy. The other axis is proportional to the dip relative to this section. So here this is a horizontal section, high anisotropy, and the axis is vertical.
Yeah.
Okay, here is you know, if the fabrics are parallel to the section, they collapse into a line. Okay. What happens if you apply, you do the teleseismic tomography? This is the plume, yeah. So this is only using synthetics computed with only the isotropic component of the elastic tensor, right? And these tests are done, for example, to show trade-offs, right? You see that you get a small amount of seismic anisotropy, which results anyway, okay, which appears here when you do inversion for anisotropy.
Yeah.
But the point is that this strong low velocity anomaly, which was confined between the surface and 100 kilometer, gets smeared
They get smeared
all
out.
across the upper mantle. Because you're sampling it only using these teleseismic phases, this is an horizontal layer, and where do you want to put the low velocity anomaly? And so what happens is that the inversion ends up in distributing the low velocity anomaly everywhere. And so that's where you need other phases.
I see you need surface waves too. Then.
Exactly, yeah. And also when you include for seismic anisotropy, you do manage to recover the fabrics. You see, you have this vertical and then it becomes horizontal, but the isotropic anomalies are still smeared over the mantle.
Yeah.
So and you can't avoid this problem currently.
So another kind of more
with body waves, sorry, with
surface
waves,
waves,
then
surface waves,
evolution.
yeah. The second thing when you mentioned about that, I assume that normally your anisotropy is mostly due to the strain history, maybe even the total strain.
Yeah.
But does when you introduce melts in the system, does the wetting of the grain boundaries, for example, does it completely reset your anisotropy very quickly? Do you immediately wipe out your strain history that you might record in that?
Melting deformation. There is contrasting evidence from experiments. So there was Kolstad, Holtzman that have shown that in presence of partial melting, you may get C-type olivine fabric.
Yeah.
But then more recently, there was another paper. Sorry, my name is so bad, but I can retrieve it, where they show basically different fabrics. So you get the MPO, the melt orientation, and then which has some orientation. So basically you get some fabric which is parallel to the sigma 1, and perpendicular to the sigma 3, because this is the instantaneous direction of opening of the cracks.
Yeah.
And then you have another fabric which is due to the long-term integrated deformation history. But in the end, if I'm not wrong, they in this case they see that the melt does not affect the type of olivine fabric, for example. They do see A-type. But I can check later and maybe I can say.
No, it's fine.
Yeah.
Thank you.
Anyway, for Etna, this doesn't matter a lot because I mean, there the anisotropy is so strong, 10-20%. This is P wave anisotropy, it's not even S wave, right? Because S wave are more sensitive to the presence of fluids.
Yeah.
To my knowledge, the only way to explain this pattern with the
Yeah,
horizontal
with the
slow
null,
axis
with the null discs, yeah.
is with the crust.
Yeah, yeah.
I mean, of course, in the crust, mica, phyllosilicates can be strongly anisotropic. But, you know, to explain this pattern, we should have all micas like this vertical, right?
Yeah.
Because again, the slow axis will be normal too. But you know where? We do see something at shallower depths where the slow axis become vertical. And this might be consistent with the presence of sedimentary layers, which are horizontal, you know, with some sedimentary fabric. So you have clay minerals, which can be horizontal. And then in this case, the slow axis will become subhorizontal. And that's what we see here.
Yeah.
A shallow depth, right? We know that, you know, the Etna placed over these crust. There are lots of fishoid units of the upper plate, coming from the, you know, Europe. That have been, these are locked on steroids. Yeah. Okay.
Thank you.